This plenary session, and we're going to have three different speakers about different subjects. It's a pity that our fourth speaker, Mirjana Povic, cannot do it today. We wish her just a very quick recovery. And okay, we are going to cover three different subjects, and our first invited speaker is Beatriz Sánchez Cano from the University of Leicester, and she's going to talk about the star-planet interaction, a journey through the solar system. Okay, Beatriz, the floor is yours.
Yeah, thank you, and good afternoon, everyone. Thank you so much for being here today in this talk. And I just wanted first to thank everyone in the committee for inviting me to come here. It's actually quite emotional for me because I remember my first ever talk in a conference was many years ago in this Congress. At that time, it was in Madrid. It was in the CSIC main place. But it has been quite emotional to come here after living for so long in the UK. And I have a very big responsibility, actually, because when the committee told me to talk about the star-planet interaction, so it's actually a very big topic, and it can be seen from many perspectives, from planetary science, like is my case, but also from astrophysics and astronomy point of view. But I thought I could invite you today to come with me for, like, let's say, 20-25 minutes of a journey in our solar system and understanding how is this interaction of each planet that we have nearby us with our sun, and let's see what we can learn and how we can compare the interactions between them and what we can learn that can be applicable for other planets outside our solar system. So with that, I will start my presentation, and I know this is just a very particular planet, so this is Mars, but I wanted to show an example of why it's really important to study the evolution and understanding the interaction of the sun with the planets. And I think the most dramatic case that we have in the solar system is Mars. You can see on the left a figure of Mars now. It's quite dry, no water at the surface. Well, there is ice and so on, but no liquid water. But on the right, so we have a picture of Mars in the past. Of course, it's not a picture, it's a recreation, but we have thousands of evidence that show that in the past there were abundant water at the surface of Mars. So this is for being 1 week here. That's why I mix Spanish and English, sorry for that. So we know this happens. So the key in here is understanding the interaction of Mars with the solar wind, with the sun, and it's a key for understanding planetary evolution. But it's not just Mars, it's actually all the planets. No worries, I'm not going to go through all the details in the figure on the right of the slide, but this is a very nice summary of atmospheric escape processes that happens in many planets in our solar system, including Earth, Venus, Mars, and comets in this picture. But you can see even Earth has a very abundant amount of atmospheric escape every single day. So we need to understand that because this is the key for understanding the evolution of the planets, but also is the key for understanding the planetary habitability. And habitability is really a big name nowadays in our field. And for that, I put this kind of a sketch on the right of the slide, which I like very much because this sketch can be applicable to any body. And maybe, depending on the body, you will have different blocks. But in reality, any planet can be, or any body in the solar system and beyond the solar system can be reproduced with this scheme, where you have, on the right, you have the neutral part of the atmosphere. On the left, you have the ionized part of the atmosphere. You have the arrows. Hopefully, I can show. Okay, no, maybe not. You have the arrows that came from the sun, which is the flux of energy moving into the system, and the connections between the layers. And you see on the top left, there is an interaction with the solar wind, and there are two types of interactions, and this is what I'm going to talk today. Depending on the magnetic configuration of the body, we will have a different interaction. So why to study our solar system? Because actually it's amazing. I mean, we have a very natural laboratory next to us, and we can actually go there and explore in situ. So we have bodies with atmospheres and magnetic field, as you can see here, Earth and all the giant planets. We have bodies with atmosphere, but no magnetic field, or almost no magnetic field, like Mars, Venus, or comets. We have bodies with no atmosphere, but magnetic field, like Mercury, which is now quite interesting because of Bepi Colombo. And also we have other bodies that they don't have atmosphere and they don't have magnetic field, or almost they don't have magnetic field, like the moon and the asteroids. But even more, we have another set of magnific bodies We can have everything, can have or not magnetic field, can have or not atmosphere, but they are within subsystems, especially in the giant planets. This is amazing because we have like basically all our laboratories there, just next to us that we can go and explore. And moreover, because we are talking in here, we are going through all the solar system with this interaction with the solar wind, the main manifestation of that is the aurora. So we know for sure we have aurora at Earth. Even hopefully in May you were able to see the auroras here in Spain. But also we have the massive auroras in the giant planets like Jupiter and Saturn. But you may not know that other planets like Mars has tons of auroras, like really tons of auroras everywhere on the planet. There are moons like Ganymede, which has amazing aurora. It's a moon, and it has auroras, and it's inside a system. It's inside Jupiter. So Jupiter has auroras, Ganymede has auroras, so imagine the interaction going on in here. And there are planets like Mercury with no atmosphere, so where the auroras came from? So the auroras came from the surface. We will see that later particles precipitate in the surface and produce emission of X-rays, which are considered kind of aurora. But how we are going to study this? So first, we need to understand what happened with our sun. So our sun is amazing. Okay, it's very small compared to all what we have been seeing this week in here, but it's actually amazing. So we have, depending on in here we have different filters to observe the different levels of activity that we use every day. I'm not going to go into all the details, but what I just wanted to let you know, which is important in this talk, is we know the sun can be considered as a black body, but only for wavelengths larger than ultraviolet. So if we go to the to the left part of the graphic, so we have the extreme ultraviolet and the X-rays, especially the soft X-rays, which are the most important for us because they create ionization in the atmosphere. So why I'm saying this? Because for any single body in our solar system and beyond our solar system, so if the body is nearby the star or close enough to the star and has a neutral envelope, it will have an ionosphere. And the ionosphere is the upper part of the atmosphere that is ionized because the sun or the star in particular send photons that ionize this upper part of the atmosphere, producing the ionosphere. And because the ionosphere is created because of the neutral atmosphere, is very responsive to what happened in the neutral atmosphere, as we will see later. But at the same time, because it's an ionized layer, so it's responsive to electric field and magnetic field. So it's an amazing layer that is everywhere in all the systems and really controls all the evolution of the planet. But if I'm back to the sun, so we have other features in the sun which are very important. In our particular sun in the solar system, so our sun has a different rotation that you know. So that produces that particles rotate with the planet and also, with the sun, and they escape the sun, and they escape and basically fill all interplanetary medium, which is what we call the solar wind. But the solar wind is frozen in, which sounds very weird, but it's actually an amazing property that we have. So this means the plasma from the sun moves with a magnetic field line from the sun, and they never merge with another one. So this is what you have on the figure on the right. Imagine that we are looking to the sun from above the ecliptic, so we have all the solar system below us, the sun in the middle, and you see all these lines that are like kind of spiral, so this is the Parker spiral. So they move according to the rotation of the sun, hit all the planets, but they never merge between them. And if they merge, I will show you later what happens. So when one of these lines hit a planet with a lot of particles in there, this is what happens. So this is an animation of Mars, because I thought it would be easier to show Mars because there is no magnetic field on that. So we have the solar wind coming from the right of the slide at supersonic speeds, so 500 kilometers per second on average. It could be even 1,000 kilometers or even more. It hit the planet, and when it hit the planet, so the velocity reduced drastically because it encountered the plasma from the planet. And then this is what we see, a deceleration in particles, and then a magnetosphere is created. So these are observations actually from MAVEN at Mars, but we have this for every single planet. And this is a magnetosphere, but what is actually a magnetosphere? So let's go to a classic view. So this is Earth, because Earth is a planet, even if sometimes we forget, especially in planetary conference or astronomy conference. So we have an incredible planet, which is Earth. And this is the magnetosphere. Actually, is our home in space. So everything that is inside the magnetosphere belongs to the planet. And as you can see in here, so we have at Earth a dipole. And this dipole is kind of degenerated towards the night side. So the sun, the solar wind is coming from the left, your left, yes, is coming, and is because of the pressure that is exerting on the magnetosphere, it deformates the lines, and then it elongates on the night side. But you see there are two colors. There are red and blue. So this is because in the subsolar point, we have something called magnetic reconnection. So this is when two magnetic field lines that never, ever merge, so we have the sun and we have the Earth lines, but when they have different orientations, so they can actually reconnect, and then in that case, we have an open line. So this open line is connected to the sun and connected to the planet at the same time, and are the blue ones in there. So this is what is called the Dungy cycle, and it creates the auroras. I'm not going to go into all the details, but you can see the sketch at the bottom right of the figure on the left, that this yellow band is actually the auroral oval that we have at Earth. And on the right, there is a simulation, because this is a quite live process that happens every hour. Every hour, we have a magnetic field line moving from day to the night side, producing aurora. And this is actually what happens in a normal day with normal conditions. So it's a quite dynamic motion. So this is Earth's magnetosphere, but what happened with other planets? So I like very much this sketch because it gives you, in a quick view, the size that we have in our solar system. Earth, even if we live there and it's amazing, it's actually a quite average planet, but it's not average compared to Mercury that you can see on the top left, because Mercury is very small, so we have the same kind of magnetosphere, but very, very small, because the magnetic field is only 300 nanotesla, while at Earth we have 50,000 nanotesla. But then we have the massive planets like Jupiter, Saturn, here at the bottom right. We have a massive structured magnetosphere. With they are very large, for example, Jupiter magnetosphere is the largest object in our solar system. But however, when you compare to the scale of the heliosphere, because the heliosphere is also a magnetosphere. So you have on the bottom left of the slide, so it's actually large, but it's not, of course, not large as the heliosphere. But you can clearly see the interaction with the interstellar medium, that this, again, there is a bow shock and there is a magnetosphere created by the sun. So this is the kind of structure that we are having a look today. So I'm going to start from closer to the sun to move outside to the sun, to the solar system, and I'm going to start with Mercury. So this picture that you can see there is a real picture taken by Bepi Colombo 2 years ago during the second flyby. So you know Bepi Colombo is arriving to Mercury. Hopefully it will arrive at the end of next year. But meanwhile, we are doing some flybys, and this is one of the pictures taken from one of the flybys. And we have on the top of the left of the figure, so you can see the magnetosphere of Mercury, very similar to the magnetosphere of Earth, very similar to the figure that I showed before. But on the bottom corner, on the left, so you see the magnetosphere is actually slightly different. So depending on the orientation of the magnetic field from the sun, which we call the interplanetary magnetic field, so we have actually a very dynamic magnetosphere. The structure of all the field from the planet changed drastically, and then, because there is no atmosphere, the surface properties change as well. So Mercury magnetic field is only 1% of magnetic field of Earth, very small, but it's a very highly dynamic magnetosphere. I said before, the Dungy cycle at Earth is just 1 hour, but on Mercury is 1 minute, between 1 and 3 minutes. So imagine when you take observations from a spacecraft, if you are familiar with that, 1 minute is nothing. Sometimes the resolution is that from some instruments. So it means that we need extremely precise instrumentation to be able to measure the dynamics of the magnetosphere of Mercury, even if it's a very small magnetosphere. And of course, it's populated for many particles from the solar wind, if you look at the magnetosphere, but this is just simply because of this massive interaction with the sun. This is a confidential figure, but I thought I will show you. So this is a work that we are working at the moment on Bepi Colombo. It's from the third flyby to Mercury, and it's the first time we see, so on the figure on the left, no worries for people not familiar, so these are energetic particles. But if you see the bottom two panels, so there is an increase, at the closest approach, an increase of energetic particles of 100 kiloelectron volts. So this is actually the first time that this is observed at Mercury. We believe it may be the ring current, but we are doing a lot of work on that at the moment with simulations and so on. But I said before that there were auroras at the surface of Mercury. These auroras came for particles precipitating and heating the surface and producing X-rays at the surface, which is the figure on the right. And we believe there is a link between the figure on the left and the figure on the right, but we have to demonstrate that. So this is really work ongoing at the moment, and it's only with flybys. So let's see what happened when Bepi Colombo actually arrived to the planet. So if we move now a bit farther, so we go now to the two big unmagnetized planets of our solar system, or I would like to say what originally, people said unmagnetized, because I don't think this is actually the right name in particular for Mars. So this is a comparison. On the left is Earth's magnetosphere. On the right is the magnetosphere of Mars, but actually is the same for, a priori is the same for Venus. So the scale is not the same of both figures, but you can see that the interaction with Mars, it happens much closer to the planet than with Earth. So this is simply because there is not a global magnetic field in the planet, so therefore the own atmosphere and ionosphere is the one touching the solar wind and interacting with the solar wind. So there is a direct coupling between the solar wind and the planet itself, the atmosphere. That's why the evolution of the atmosphere is more dramatic than in another planet. While at Earth, this is indirect because of the magnetic field. So for Venus, this definition is fine. Venus is a quite well-behaved planet, but Mars is not, because we have some crustal magnetic fields from the own rock. So this is magnetic field that was recorded billions of years ago, and it's still in the rocks, and it's actually, these fields are more intense than the magnetic field of Mercury. So imagine the level of magnetic field in here. So these fields actually can reconnect with the solar wind and produce a hybrid magnetosphere, and we will see that in a few slides. But there is something else. So Mars has a very elliptical orbit. So together with Mercury, they are the most elliptical orbits in the solar system, and this has an effect on the planet itself. So the interaction happens with the ionosphere, but because of this distance, the amount of photoionization that reaches, or the amount of irradiance from the sun that reaches Mars, it varies with time. So you see on the figure on the right, in green, this is the solar cycle measured at Earth. And in red, so you see the solar cycle extrapolated to Mars distance. So this is actually what you see at Mars. You see a sinusoidal variability, which is the effect of the own orbit. And when you look to the ionosphere, so on the figure at the bottom, so this is the total amount of electrons that we have in the ionosphere. So you can clearly see the same variability. So the ionosphere has this variability, and as a consequence, all the boundaries of the system, so for example, on the top panel now, we have the bow shock, which is the most external boundary on the figure on the left, so the first one that we saw in the previous slides. So it follows exactly the same variability. So this is a unique characteristic of a magnetized planet that for sure is not seen on planets with intrinsic magnetic field as Earth. So basically, the sun, the solar irradiance, is the factor controlling all the system. So this is very important, of course, when considering atmospheric escape, etc. But as I said before, Mars has strong crustal fields at the surface. So this is the map of the location where they are. So they are mainly in the south hemisphere. So these are the red, where the red colors are is the most intense magnetic fields. So you see the scale, like in orbital scales, is 700 nanotesla, so much more than for sure than Mercury. And this is one of my favorite figures. So what happened in the ionosphere? So actually, when you look to the total amount of electrons that you have in the ionosphere, to me, it's amazing. I can clearly see the magnetic fields there in the ionosphere. So there is a lot of modulations that we need to take into account when considering this planet. And this is more important because I said before, there are tons of auroras at Mars. You may not know that, but actually, there is a high probability for the astronauts to see auroras everywhere on the planet. So we know there are discrete aurora, same as Earth, but on the crustal fields. We know there are diffuse aurora, which are produced when there are showers of energetic particles from the sun, so the full planet glow. It's like a full illumination, full green planet. And then we know also there are auroras on the day side. They are also at Earth, but at Mars, they are very seasonal effects, which are the proton aurora. But moreover, since last year or 2 years ago, so we know that actually there are more types of aurora that we didn't know before. So thanks to the Emirates mission that is on Mars since a few years ago, so we have detected this kind of auroras that you can see there on the figure on the right. So this is on the north hemisphere of Mars, far away from where the crustal fields are, and you see the kind of feature, sinusoidal feature that you can see there. So this is what we call the sinusoidal aurora, which is basically a discrete aurora, but far away from the crustal fields. So there is no explanation to that. It's not related to what happened at the surface, but it's related to what happened at the tail of Mars. And this is a unique feature of this planet. So this is a cartoon that explains very well what is going on. On the left is the well-behaved Venus, just the magnetic field from the sun draping and creating a magnetosphere. On the right, Mars, still with magnetic field draping from the sun, but because all the crustal fields, so they interact between them, they interact with the solar wind, and then they produce a kind of party of fields in the night side, and we have an amazing ionosphere, and we have an amazing aurora observations thanks to all these fields in the tail of Mars. So that's all for Mars, but I could not finish because you may know, like, my involvement in the mission at the moment. So the future of Mars is really 2 spacecraft at least there, because we cannot do science without that. That's why there is a mission at the moment from NASA, a very small mission called ESCAPE that is going to be launched this year. But also, I'm proposing together with a very large, amazing team in Europe, we are proposing the mission EMMATIS to the European Space Agency, which is at the moment in phase A in the competition, only and exclusively to resolve this problem. But enough about Mars. So we move now a bit further. So what happened with comets? I will go a bit quick here because this interaction is actually very similar to Earth and Mars, to Mars and Venus. They don't have magnetic field in principle, at least the ones that we have studied, they don't have magnetic field, but they have massive atmospheres. So you know when they arrive close to the sun, they start to develop the coma, they start to develop the tail, so they have a dust tail and they have an ion tail. And this is what we see in the evolution of the periapsis of the orbits through the sun. Their interaction with the sun is exactly the same as Mars and Venus, so we typically compare, but there are 2 main differences. So there is not atmospheric circulation, which is very important when studying the ionosphere of the comet, and also the gravity is very small, typically because they are just rocks in space. So this means that the boson and the magnetosphere are much massive than they are, for example, with Venus and Mars. But the interaction is the same, but I just wanted to show at least one slide just to show you, like, we don't forget the minor bodies in the solar system. And there is also another body nearby us, is our moon, which also has a very peculiar interaction, very different to everything that I showed before. So you know, because of the orbit moon, so the orbit of the moon, so for part of the orbit is inside our magnetosphere. But when it's outside the magnetosphere, so it has a peculiar interaction with the solar wind, and this is because there is no atmosphere, so the particles hit the surface directly, and most of the composition of the surface is actually affected because of these particles putting on the surface. And we have a kind of wake behind the planet. And this is simply because of the interaction, so the solar wind is draping through the moon and basically hugging the moon. But also, same as Mars, but less intense, the moon has crustal magnetic fields at the surface. And there are kind of mini magnetospheres happening in the surface of the moon. Much less, weaker than at Mars, but they are still there. And they have also the same kind of interaction locally that Mars has with the solar wind. But now I go to the giant planets. So this is literally another world. So this is something totally different. It's actually, to me, I think is really amazing how all the subsystems behave together. So I want to start with Jupiter, but I said before, if you remember, that the magnetosphere of Jupiter is actually the biggest object in our solar system. Unfortunately, we cannot see the magnetosphere because it's just transparent, the plasma is not visible. But if this is a picture actually that you can find on the ESA website. So if the magnetosphere of Jupiter were visible, so this is how big it will look like. So, and Jupiter is at 5 astronomical units of distance, so it's really far away. But this is how big it is, that even we could see that with our naked eyes if it was visible. So it's a massive structure. Same when looking to the scheme, it's very similar to Earth, but just bigger. It has 20,000 more times magnetic fields. Of course, it's bigger, it's massive. That's why the radiation environment at Jupiter is so big. But also, you can see that there's a kind of deformation. So there is something in the middle that is a kind of deformation. So the lines, the magnetic field lines, are not as circular as they were for Earth or for Mercury. So also, it's very big because the solar wind is 5 astronomical units, so the solar wind is weaker there. So this means that it only feels 4% of the pressure that Earth feels. But also, it rotates very quickly. So that's why there are big auroras, because the magnetosphere rotates, so the planet rotates very quickly, the magnetosphere as well, and then the particles trapped in the magnetic field lines, they precipitate quicker to the atmosphere. So that's why the auroras are so bright at Jupiter and the same at Saturn. But this is actually when we do a close view of the planet, so this is actually what is going on. So that's why the magnetic field lines are deformed, because the moons, the Galilean moons, are interacting with the magnetosphere in very complex ways that we are going to see now with a simulation. But the main moon is Io or Io, depending on how you want to call that. But Io is a volcanic moon, and it shows it ejects a lot of material into the magnetosphere. And this material became trapped by the magnetosphere, and it forms a torus of plasma surrounding Jupiter. There is another moon, which to me is my favorite, and is Ganymede, and it's my favorite because it has a magnetic field. But moreover, we know there is an ocean below the surface, and the ocean is conductive, so it creates also a magnetic field. This magnetic field creates auroras, but at the same time, it's connected to the magnetic field of Jupiter. So I think it's the most complex interaction in the solar system. The moon itself is great. It's bigger than Mercury. It's the largest moon in the solar system, and the interaction itself it makes an amazing world to study. And actually, this is one of the main objectives of the JUICE mission, as you will see in the next slide. So this is actually a simulation that the JUICE team provided me for the presentation. So you can see Jupiter, and we are going to see the 4 Galilean moons. So the most external one is Callisto, which has also some interaction, but this is the one that we know the least at the moment. But then you will see Ganymedes appearing a bit closer to Jupiter. And then you will see the interaction of the own magnetic field from the moon with the own magnetic field from Jupiter, and the creation of auroras at both planets. Sorry, the planet and the moon. Actually, it will be amazing to me as a scientist. It will be amazing to understand if both auroras are produced at the same time and what is the connection between them. Then we have Europa, which is one of the most peculiar moons in the solar system, one that is there is highly probability to find habitability or conditions for habitability. And then we have Io, which is the moon that I said before, that you will see ejects all the particles from the surface that go to the magnetosphere and creates the torus surrounding the planet of the moon. So I will go a bit quickly because I think it's already time to finish. Saturn is very similar, so I'm not going to go into all the details. Saturn, instead of Io, it has Enceladus, but it's the same process, very similar. And actually, the next L4 mission, the selected by ESA, is to go to study this moon and interaction with Saturn. But also, there is another moon very interesting in there, which is Titan. So Titan, in principle, is inside the magnetosphere of Saturn. And it doesn't have magnetic field, and it's interacting with the planet just in a kind of, subsonic way, because it's inside the magnetosphere. But from time to time, you can see with the circle, it goes outside the solar system. Sorry, outside of Saturn's system. So this is because there is something in the solar wind, like high pressure, that presses the magnetosphere, and the moon can go outside. So in these conditions, which has been one time only observed by Cassini, and it was on the 1st of December of 2013. So it passed from the figure on the top, which is the normal way in which it interacts with two winds. So imagine you are in your car, and you go against the wind, and you have the separation of winds. So this is the normal interaction. But it went, during that time, outside the system of Saturn, so it went to the figure at the bottom. So basically, it went to be like Mars or Venus, just in the pristine solar wind. And this is my last slide, I promise, so I'm just finishing here. I want to just say very briefly, so we don't know much about the farther planets, Uranus and Neptune, but we know they have a very funny rotation, as you may know. And because of that, even if the magnetosphere is expected to be similar, because of that, so we know it's going to be very difficult to understand, because this rotation of the axis of the planet with the magnetosphere is going to create an elliptical structure, which I don't have any idea at all of how the plasma is going to move in here, but we really need a mission to go there to understand this. So to me, the take-home message from my talk today is like, we really have a unique solar system. It's a natural laboratory and it's there for all of us to go and explore. There is a high, intense link between planetary and heliophysics, and this is very, very important for understanding the habitability of a planet. But also, it's the same for any exoplanet. So we have kind of all planets here. I'm sure there is much more worlds with different conditions outside our solar system. So we have to understand pretty well our solar system to be able to compare and understand processes beyond. And then this is what I just said. So it's very important for understanding planetary evolution and habitability. And for sure, we don't have enough missions. So we really need more missions because the mysteries that we have just in our neighbors' planets are still unresolved, and we even don't know, I will say, 1% of all what they can show to us. So yeah, thank you very much again for your time.
Okay, thanks a lot for this very nice talk, really. I am sure there will be questions. Okay, who wants to start there, please?
Thank you for the talk. I was wondering whether you can learn about the internal core structure of the moons and planets due to the magnetic fields.
Oh, definitely. Like, for sure, this is one of the goals of Bepi Colombo. So Bepi Colombo has a very complete suite of instruments for surface and gravity and everything. But by understanding what happened in the magnetosphere, because we know the magnetosphere is connected directly to the surface, we can understand if there are telluric currents inside, we can understand about the structure, internal structure of the planet. And the same happened with other planets, like, for example, on the mission that I'm proposing to ESA, we have 2 spacecraft. So with that, we can actually do, for the first time, understanding if there are currents induced in Mars' surface, because we have 2 magnetometers that can go information and study the currents. So there is a lot of possibilities that can be done, and I'm sure it's the same with the giant planets, for sure, because thanks to the magnetic field, we know they have oceans under the surface. So for sure, you can learn about the planet itself and the system itself just by studying the interaction with the solar wind.
Any other question? We cannot see anything from here.
It's like totally blind.
Okay. Let me ask you. Yes, I was impressed with the results you saw also by Bepi Colombo with this flyby. Really, can you give more details? And then what do you think that we will be able to be observed when Bepi Colombo is already working?
Yeah, it's actually amazing because it's just a flyby and everything happens very quickly, I have to say. But it's because previously it was only properly studied by MESSENGER, and the orbit of MESSENGER cannot map very well the magnetosphere. So only with the flyby, it passed by areas that it was not explored before, so that's why we could see these particles. And we think it's the ring current of the magnetosphere, which I did not explain today because it's a lot of features in there, but it's basically the particles moving surrounding the planet in the magnetosphere. And it's very difficult to prove because with the flyby, it's just all the instruments at once taken, and at the moment, the 2 spacecraft are together. But once they separate, it will be great because then we will have one spacecraft monitoring the solar wind and the other one monitoring the magnetosphere. So then we could actually do comparisons in 2 different points of the system. But at the moment with the flyby is what we have. So we do science, but not magic, basically.
No, but you can do science already.
Oh, yes,
That is
yes.
very, very amazing. Okay, thanks a lot, Beatriz. You know that this summer we have beautiful auroras here in Calar Alto even. There are very nice pictures. If you want to go to the webpage of the Calar Alto Observatory, you could see the images of the auroras. Okay, thanks a lot.
Thank you.